Okay, so yesterday we talked about finite dimensional. Too loud? What should I do? Yeah. Well, yesterday we talked about finite dimensional integrable systems. Today, is it still too loud? Okay. Yeah. Today we go back to the KdV equation, which I recall is an equation on a function of the x variable, which we think of as a spatial variable, and the time variable t. And the equation has this form. So today we'll see that, or I'll try to convince you in the next two lectures that this can be viewed also as an integrable system. Well, first of all, if we want to think of this as a vector field or an ODE, of course, here, well, we actually have a u that depends on x and t. One way we can think about it is it's a function of x that evolves in time. Therefore, we think of it as a vector field. It's a vector field on a space of functions. The space of functions is infinite dimensional. So integrability here in particular will mean that this has infinitely many conserved quantities, or infinitely many first integrals. So we want to see why that's the case. And we'll also see that it's a Hamiltonian system. So it fits into the setting that we were discussing yesterday. So we're going to start with something simple. Let's first see that, well, indeed it has some first integrals, that some things are preserved. And actually, well, before we do any of this, for this makes sense, to make sense of this being an integrable system, one actually needs to introduce boundary conditions, because in this generality that's not true. So we cannot allow u to be any function. There should be some conditions on u. The two standard settings, one setting is that u is a function that's as a function of x that's rapidly decreasing at infinity. Another possibility is to require that u is periodic. So we'll do the periodic case, but most things we'll discuss, they work in a similar way in both situations. So u is going to be a function that's periodic in x with period 2 pi. So this is now a flow on the space of 2 pi periodic functions. And that's our manifold M on which the dynamics takes place. I'll denote this as C infinity of S1, because 2 pi periodic functions, you can think of them as functions on the circle. We require that our functions are infinitely smooth. So that's our phase space. Because this M is a vector space, the tangent space to M at any point can be identified with the same thing. Also C infinity of S1. Moreover, the cotangent space will also identify with the same thing, so that's also going to be T star of M at some point, so here. And, well, of course, T star of M is supposed to be the dual of this space. The true dual of this space is the space of distributions, but well, as often happens in infinite dimensional geometry, we do not want to consider this whole huge dual space. Instead, we restrict to an appropriate subspace, and here the subspace is going to be also the space of 2 pi periodic functions. The way it works is that if you have a function u that you think of as a tangent space element, and another function that's the cotangent space element, you pair them by integrating uv over the period. So on our tangent space, we introduce L2 inner product because we have inner product that sort of identifies tangent and cotangent spaces. We think of them as the same space. as was said, that's not the true dual, but that's the dual that we'll be considering. So now we have this. Well, eventually we'll see that this is a Hamiltonian system, that this has infinitely many first integrals. Let's start with something simple. Let's see that, well, some things are actually preserved by this flow, just in order to understand what it means to be a first integral for the KdV equation. So for instance, and so here our phase space, our M is the space of functions. So first integrals, they should be functions on that space. They should be functions of functions. So for instance, let me consider a function f1 of u that's defined as the integral of u over the period. So that I claim that this thing is preserved by the KdV equation. So this is one of the infinitely many first integrals of the KdV equation. To verify that, we just need to check that the time derivative of this along the KdV flow is preserved. So we differentiate with respect to time. Of course, that's the same as differentiating this u here with respect to time, because integration is with respect to x. This becomes integral from 0 to 2 pi with a negative sign of 6 ux plus u triple x. And we need to show that that's 0. The reason why that's 0 is because the expression which is written here is a full derivative of something. Specifically, it's 6 u squared plus u second derivative, and then differentiate with respect to x. So because it's the full derivative, the integral of this is going to be the difference of the values of the function at 2 pi and 0, because everything is periodic, that is equal to 0. Yes.
You have a question?
I have 3 fingers. I think it's 3u squared.
Yeah. I would agree. Thank you. Okay, so we see that indeed this f1 of u is a first integral. So that's preserved by the KdV equation. So one first integral here we could just guess. In the same way, one can verify that f2, which is the integral of u squared over the period, is also a first integral. You do the same thing. You differentiate u squared with respect to time, and you see that the expression you obtain is a full derivative of something in x, therefore the integral is equal to 0. So we have 2 first integrals. Naively, one could think that maybe f3, and we hope to eventually get an infinite sequence of first integrals. So maybe f3 is equal to the integral of u cubed dx, but then you differentiate that, and that doesn't work. So when you differentiate u cubed with respect to time, the expression you get is not going to be a full derivative, and therefore this thing is not going to be preserved by the KdV equation. So 2 integral of u and u squared, they're preserved. The integral of u cubed is no longer preserved. So at this point, this pattern breaks. We need to do something else. So the next first integral for the KdV we'll find as it will actually be the Hamiltonian function, or the energy for the KdV equation, and simultaneously we'll therefore show that it's actually a Hamiltonian system, because it can be written as the Hamiltonian flow of something. So the setting for this will be, so as we discussed yesterday, we may consider Hamiltonian systems on symplectic manifolds, but also on Poisson manifolds. So the Poissonian setting was as follows. So we have a manifold M. A Poisson bracket is an operation on functions on M, which turns functions into Lie algebra and also satisfies the product rule with respect to multiplication of functions. And as we discussed, any such Poisson bracket is given by the formula f. The bracket of f and g is some bivector, which in general depends on the point, applied to the differentials of these functions. That's what any Poisson bracket looks like. Conversely, one might ask if anything like that is a Poisson bracket.
Well, actually, you don't get that automatically in your case. You have to assume it's of infinite dimension, everything is not precise.
That's right. Yes. So, that's a finite dimensional result. In the infinite dimensional setting, it will only work under some quite strong assumptions. But here we're just, for now, we're trying to generalize our finite dimensional intuition.
The loop group, then it is state. Because for the loop group, it's like nuclear pressure space. It's model on nuclear pressure space. Smooth loop group. So there, all the derivations are in fact effortless. Then you look at this existence of.
Yeah. But I mean, here we're not trying to prove any result about all Poisson brackets. We just want to introduce a Poisson bracket for the KdV equation. So when we go back from bivectors to Poisson brackets, so suppose pi is a bivector, then we define a bracket like this. This will satisfy all the axioms of the Poisson bracket, except possibly the Jacobi identity. If you write this thing in general, it doesn't satisfy the Jacobi identity. The Jacobi identity is some partial differential equation on this bivector pi, which doesn't have to be satisfied. One particular case when it is for sure satisfied is when pi does not depend on the point. So if we have a bivector on a vector space that does not depend on the point, so we just define our bracket by the formula pi of df dg, then that's going to be a Poisson bracket. So for the KdV, we will have a Poisson bracket which is exactly of that form. So to get the Hamiltonian representation for the KdV, we will rewrite it in the following form. We already observed that this expression here is the complete x derivative of something. We used that when we showed that the integral of u is preserved. So let's just write it in that form. So this symbol I'm going to use for the x derivative. So ut is the negative derivative of 3u squared plus u double x. So let's write the equation in this form now. And going back to this Poisson manifold setting. So when we have such a Poisson bracket, then the way we define Hamiltonian vector field is simply by pi dh. In the symplectic setting, that was omega inverse dh, but now we no longer assume the existence of the symplectic structure, so we simply pair the differential of the Hamiltonian with a Poisson tensor. That's our Hamiltonian vector. So my claim is that, well, this is exactly what's written here. Specifically this, well, maybe negative sign I put inside. So the claim is that this delta here, that can be viewed as a Poisson tensor. And this expression here can be viewed as the differential of a certain Hamiltonian function. So indeed, let's see why that's the case. So first the Poisson tensor. The Poisson tensor, it's a bilinear function on covectors, which one can also view as an operator from the cotangent space to the tangent space. That's the way we see it in this equation. The corresponding Poisson bracket is as follows. So the bracket of f and g, and here f and g are functions on our phase space, on the space of functions. The bracket of f and g is equal to integral of df, And df is going to be a function because we identified our cotangent space with a space of functions. Then we take the x derivative of dg times dx, integrate over the period. So the claim is that this is a Poisson bracket on M. So the reason for that is, well, that's clearly skew symmetric because we can integrate by parts, move this differentiation to the first argument, it's going to acquire a negative sign. That's just integration by parts. As for the Jacobi identity here, it's satisfied for trivial reasons because here, well, this delta, it's a constant Poisson bivector. It doesn't depend on the point. As was said in that situation, the Jacobi identity is always satisfied. So this is indeed a valid Poisson bracket on the space of functions. And this delta is the corresponding Poisson tensor. So that part is fine. Now we need to verify, yes.
If you have F1, F2, how do you multiply these two?
You don't multiply these objects, you multiply their differentials. When you compute differential at a point, that's an element of the cotangent space. The cotangent space, we identified that with the space of ordinary 2-pi periodic functions. So these things here are just ordinary 2-pi periodic functions of x.
And then how do I write the product rule?
Why do you apply the product rule?
Because you say it's a Poisson bracket. You need also the product.
Oh, I see. Well, you multiply these two things in an ordinary way, just how you multiply any functions. Well, what you're saying is that it's not going to be in the form integral of something. Yeah, sure. I mean, this problem always arises in the infinite dimensional setting. What is the appropriate algebra of functions that we need to consider? And yeah, so maybe one would want to consider local functionals like this, but then it's not closed under taking properties. Yeah, so there are technical issues there, which, well, it's not sufficient to consider functions like this. You may also want to allow polynomials of those things.
This is like with parents. It's enough to be sufficient a good father.
I guess. Okay, so now we want to demonstrate that that's the differential of a certain function, h.
So you need that df in a point u is still a reasonable function x.
Yes. So again, well, Poisson brackets on infinite dimensional manifolds, they are usually defined on some subalgebra of functionals or subclass of functionals, which...
Can you give an example of a subclass where it's okay?
Here?
Yes.
Well, for instance, if your function is an integral of a polynomial and u and its derivatives, then it's okay.
So polynomials and integrals. Yes. Polynomials.
Integrals of polynomials, I'd rather say, but you can do polynomials of integrals.
Polynomials and integrals of reasonable functions in u.
Well, I'd say integral over the period. Here you have some function that depends on, well, a polynomial function of u and its derivatives. That is certainly okay. And the problem with that is that that's not an algebra, that's not closed under multiplication. If you want an algebra, you will also allow multiplying such things together.
Totally, I also couldn't understand that. So for example, like F2, what is like dF2 as a function of x, which is to be put inside the integral with the definition of Poisson bracket?
Maybe the definition of the Poisson bracket was what I just erased.
Yes, and in that you got like df as a function of x. Yes.
So df is a function of x. Yes.
what is df2 for this f2, for example?
Well, you have here, you compute Poisson bracket of f and g. It's equal to
Like partial dg is clear because this is just a number. I mean, like this is just a function of x.
yes, these are all just functions of x.
Partial dg is, I mean, like if I understand.
Partial means partial with respect to x.
Yes. So like and dg seen as a differential, then partial of dg makes sense as a function.
Yes.
Out of that, you got
u. Then it's easier. dg is evaluated in a function u.
Well, we evaluate
Still a function of x.
Poisson bracket at u. So here we take the differentials also at u. So this will all be functions of x. I'll do a calculation right now. Maybe that will clarify it a little bit.
yes, yeah, got it. Okay, so the UF is just f prime in the usual sense.
Yes, but he assumes that duf and dug are still reasonable as interpreted as a function. It's not an arbitrary distribution, as you might think.
Distributions given by smooth functions.
Smooth is maybe not necessary, but
This Poisson bracket is only defined if the differential is actually a function.
smooth is not necessary. It's just you need to integrate in the end.
But for instance, like for linear Poisson bracket, it's enough to know the bracket for linear functions. The rest is automatic.
Yes, but that's probably not true in infinite dimensions.
Not in this case, but this shows that it's enough to have sufficiently many good functions.
Okay, so I was hoping to show that that's a Hamiltonian equation. For this, we need to show that that's the differential of a function. So let me give you the function and hopefully convince you that that's indeed the differential. So first term is rather clear because it's negative 3u squared. We will have integral of u cubed, and that's from 0 to 2 pi. That will give us the first term. Okay, yes, it's negative. And to get the second term, what we need to consider is plus 1/2 ux squared dx. So let's compute the differential of this h. So h is a function of u. To compute the differential, you add epsilon times v, expand that, and epsilon take the linear term. That's what's going to give you the differential. So here, I replace u by u plus epsilon v. It's cubed. So if I look at the term that's linear in epsilon, that's going to be 3u squared times v. So I get the integral of 3u squared times v dx. That's a linear function on the space of functions. That's a linear function on v. This linear function is given by pairing with 3u squared. Therefore, the differential of this first term is indeed 3u squared, or negative 3u squared. Then you do the same with the second term. Here, this ux squared, the linear term is gonna be ux vx, which well, you need to rewrite as pairing of something with v. For that, you integrate by parts. When you integrate by parts, you move this x derivative to u. We got u double x with the opposite sign paired with v. Therefore, the differential is u double x. I think I confused all the signs, but up to sign, what I said is correct. So indeed, we see that that's the Hamiltonian for the KdV equation with the Poisson bracket just given by the differentiation operator. So does that clarify the concerns that were raised earlier?
Yes, I think so. Yeah, thank you.
Okay, and we also see that, so we initially showed that the integral of u is preserved, that the integral of u squared is preserved. We were hoping to generalize this to sort of an infinite sequence of first integrals, but the naive attempt to do so didn't work. The integral of u cubed is not preserved. But we see what is preserved is the integral of u cubed minus 1/2 ux squared. So there is a sort of a correction term that needs to be introduced. And hopefully same thing can be done with kind of higher powers of u so that we get an infinite sequence of integrals. But clearly here we need some technology to produce this. We cannot just be guessing them one by one. We need some machinery that will actually produce an infinite sequence of integrals. And also eventually we'll need to show that this integrals Poisson commute with respect to the bracket that we introduced. So what we'll do first, there are different approaches to this problem. So first we'll discuss an approach that from which we'll see that, yes, there are infinitely many conserved quantities. It will not be so easy to see why they Poisson commute, but about that we'll talk later. For now, we just want to find infinitely many conserved quantities for the KdV equation. Do I have, yeah, it's, okay. Now that's, and the idea that we will use is based on the so-called Lax form of the KdV equation. And what we'll see is that the KdV equation is actually closer related to the spectral theory of the following operator. We take this operator of taking the second derivative with respect to x and add the operator of multiplication by the function u. So this operator, it's commonly known as Schrödinger operator. Also in the periodic setting, it's called Hill's operator, but I guess in this institute we need to call it Schrödinger's operator, so let's just stick with that. And what I'll now show is that the KdV equation is closely related to the spectral theory of this operator, which we will denote by L. And to see that, we will write the KdV equation in what's called a Lax form. So in general, a Lax form of an equation is a differential equation which has the following form. So suppose we have L, which is an operator on a certain space, maybe on a finite dimensional space, then it's just a matrix. And additionally, this operator depends on the time variable t, so that I can differentiate this L with respect to time. And well, when I differentiate an operator with respect to time, what I get is again an operator, and suppose that this operator can be written as the commutator of L and some other operator A. The right-hand side here is just the usual commutator LA minus AL. So this equation here is known as Lax equation. So what's the main feature of the Lax equation is that this equation, it defines what's called an isospectral deformation. So the claim is that this equation implies that the spectrum of L is preserved. Well, of course, for that to make sense, we need to actually say on what space these operators act to make sense of the spectrum. So in the simplest case, assume that L is just a linear operator on a finite dimensional vector space, in which case it's a matrix. In that case, it's almost trivial to see why the spectrum of the matrix L is preserved. For instance, first let's see that the trace is preserved. Take the trace of both sides here. This is a commutator. All commutators have zero trace. So the trace of the right-hand side is 0. The trace of the thing on the left is the time derivative of the trace of L. And that is equal to 0. So if we have this equation, the trace of L is preserved. Of course, I'm assuming it's finite dimensional, otherwise trace may not even make sense. But also another elementary calculation shows that if L satisfies a Lax equation, then any power of L satisfies the Lax equation with the same A. So this is a simple computation. Just take the time derivative of L to the power of k using the product rule. You'll see that it satisfies the same equation. What this implies is that the trace of that thing is also preserved, also doesn't change with time, because it also satisfies the Lax equation. So we see that the traces of all powers of L are preserved. Therefore, the eigenvalues of L are also preserved, because traces of powers, they're just elementary symmetric functions of eigenvalues. So indeed, this equation defines what's called an isospectral deformation, at least in the finite dimensional setting. This can also be verified in many other settings, not necessarily finite dimensional. I just wanted to show this simple argument that works in the finite dimensional case. One can actually show more here. As L evolves with time, it stays in the same conjugacy class. That's a slightly stronger statement than the spectrum being preserved. Actually, the Jordan normal form of L also remains the same. So in this this idea of the Lax equation, it's actually a common source of integrable systems, because, well, if we have an equation like this, it automatically has a lot of conserved quantities, namely the traces of powers of L or the eigenvalues of L. And, well, in many cases, that's enough to ensure complete integrability of this equation for many finite dimensional systems. But here, we care about the infinite dimensional case, about the KdV equation. So let's show that the KdV equation also admits the Lax form. So here our L is no longer going to be a matrix, but it's going to be that Schrödinger operator that we introduced, p squared plus u. And well, A is also going to be a differential operator. In fact, what that differential operator should be, one can sort of, is a nice exercise. So suppose you don't know the KdV equation, you don't know what it looks like, then you just want an equation that has this Lax form with L being the Schrödinger operator. Then what one can show is that, I'll do a calculation in the simpler case, but what one can show is that, well, here we want A to be also a differential operator. If that to get the KdV equation, clearly we need third order differential operator to get the third derivative. So the claim is that, well, if we want the equation to have this form, then KdV is more or less the only thing we can have. So let me show you how that works. And actually, this idea, one can also use it to produce many other integrable systems. You just look for equations that can be written in this form using differential operators. You change the degrees of these differential operators, you get a lot of integrable PDEs. So let me show you how that works. So I want an equation that looks as follows. The time derivative of the Schrödinger operator is equal to the commutator of the Schrödinger operator and something else. So for instance, well, that something else should also be a differential operator, so that I can compose these things, take the commutator. So let's consider the simplest case when this operator is of degree 1. So maybe it has the form delta plus v, where v is some function. So I want an equation of this form. This will not give me KdV. What I want to show is that, well, if we want this equation to be consistent, this will tell us what this V should be. And then doing the same thing for third order operators, we will obtain the operator that corresponds to KDV. So let's do a calculation here. So here I'm supposed to take the commutator of these two operators. So the commutator of delta squared and delta, that's equal to 0. They clearly commute with each other. So then the commutator of u and v, that is also equal to 0 because, well, there's some multiplications by functions, they also commute with each other. So we need two commutators. One is the commutator of u and delta. So that's u delta minus delta u. So what is delta u? Delta u is an operator when you first multiply by function u and then you take the derivative. That's the same if you want to multiply by function and then take the derivative, that's the same as do it in the other order and then add the derivative of the function u. That's the product rule. So these two terms cancel out, and we see that the commutator of u and delta is equal to negative ux. In the same manner, we compute the commutator of delta squared and v, and that will be v second derivative plus twice vx delta. That's the other commutator that we get from here. As a result, we get this three terms. Then we look at the left-hand side of the equation. The left-hand side of the equation, the time derivative of delta squared, that's 0. Delta squared does not depend on time. So on the left, what we have is a function. That's the time derivative of u. Because the thing on the left is a function, the thing on the right should be a function as well. It should be a degree 0 differential operator. Otherwise, what we get is not a consistent equation. Because of that, this term should be 0. So v actually needs to be a constant here. And clearly, without loss of generality, one can just assume that v is 0, because while taking a commutator with a constant is a trivial thing. It doesn't do anything, so one can always subtract or add any constant. So as a matter of fact, the only non-trivial degree 1 operator that we can have here is just delta. One could do a slightly more general thing, assume that this delta has a coefficient, which is a function, then the same calculation would show that that coefficient is also a constant. So there's not too much freedom here. So v is equal to 0, so these terms disappear, and as a result, this Lax equation, that's simply the equation ut is negative ux. Up to sign, that's a linear PDE that's known as the wave equation. So if we write the Lax equation with L being the Schrodinger operator and A being a first order differential operator, then the only thing we can get from that is, it's not very interesting, it's just a linear wave equation. And then one can do a similar thing, but now allowing A of higher order. So the next case is when A has order 2, and there is one case that definitely gives you a consistent equation, namely A can be equal to L. A can be delta squared plus U as well, but then we get an equation that's trivial. There is no dynamics here because L and A, they commute with each other. And then using the same kind of calculation, one can, this A is not unique because you can also rescale it, of course. And what you can also do is you can add this first order thing that we obtained previously. Up to that, there is nothing else you can do, yes.
A allowed to depend on you?
Say it again?
A allowed to depend on you?
Yes, sure. A is allowed to depend on you. A is allowed to be anything. The only thing we assume here is that an equation is consistent. And just from that consistency for first order, we get that the only thing that's allowed here is delta, plus possibly a constant, which is irrelevant. For the second order, you get that the only thing that's allowed is this A plus a constant multiple of delta. So up to this first order thing, there is a unique second order thing that we can have, and that gives you trivial equations. Then you go to order 3, and for order 3, you obtain that again, there is just a unique A that works, that gives you a consistent equation up to things of smaller order. It's not quite unique because you can always add multiples of L, you can add multiples of delta, which give you the wave equation. Up to this, there is just unique A that produces a consistent equation. That A looks as follows. So the first term is delta cubed. I just normalized for this coefficient. I want it to be 1. Then it's plus 3/2 U delta plus 3/4 U prime. So that's the only A which gives you a consistent equation up to smaller order things. This looks complicated, but it's a simple computation to see that, well, that's the only thing that works, yes?
I know you've said this already. What is the reason why the B had to be constant when you did a first order? What makes that not consistent?
So if you have V here that's non-constant, then this commutator is going to be a first order differential operator. The thing that's wrong with that is that the left hand side is a zero order differential operator, so they cannot be equal. That just doesn't define a valid equation. It's, well, I mean, it doesn't have any solutions, if you like, because you get an equation that 0 is
But the commutator is in general by 1 smaller than the sum of
That's
degrees.
right, but that's not enough, right? Because here the sum of degrees is 3, so the commutator is automatically of degree 2, but you actually want it to be of degree 0, because otherwise you will get that some differential polynomial of u is equal to 0, so there's no dynamics. There's basically a finite dimensional space of u's where you, that's not there. Does that answer your question?
This u prime there is ux.
U prime is ux. Yes. So as I said, this thing here is just the result of a simple calculation. Just the same as we did for the first order. That's the only up to the small order things, and assuming this coefficient is equal to 1, and it has to be constant. So we can always rescale for that to be 1. That's the only thing you can get. And then, well, if you look at the corresponding Lax equation, that's going to be precisely the KdV equation, I think up to the factor of -4 or something like that. So to get the KdV equation, maybe one needs to take -4a or something like that. But that doesn't matter because that's just time rescaling. So when you multiply a by a constant that corresponds to rescaling of time, that's not very interesting. So that's also a way, well, what that shows, first it shows that the KdV equation indeed can be written in the Lax form with L being this and A being that. You can also go the other way around. Just take the commutator of L and A. You'll see that that's a 0 order differential operator. So that's multiplication by a function. What the function is, up to a constant, that's precisely u6ux plus u triple x. That's what you see in the KdV equation. So the KdV equation is a Lax equation. Moreover, if you want a Lax equation with this being differential operator of degree 2, this being differential operator of degree 3, the KdV equation is pretty much the only thing you can have. As I said, in this manner, you can get, yes, so before we go to that, so why does this imply infinitely many conserved quantities? Well, because as we demonstrated in the finite dimensional setting, and as can be shown in our infinite dimensional setting, it follows from this that the spectrum of this is preserved. So the spectrum of the Schrödinger operator is preserved. Well, if we didn't have any boundary conditions, then the spectrum of the Schrödinger operator would be the whole real line. That would be a trivial statement. But because we assumed, so what is the spectrum of the Schrödinger operator? Well, you solve for eigenvalues. So you want this applied to a function f equal to lambda f. For most values of lambda, this equation, it will not have periodic solutions. And there is a discrete set of lambdas for which you have a periodic solution. That's the spectrum of the Schrödinger operator. There are countably many eigenvalues. For instance, if you take u to be 0, you get the equation f double prime is lambda f. The solution to that is given by exponentials or trigonometric functions. If you want that to be 2 pi periodic, lambda needs to be 0 or negative complete square of a natural number. So there's discrete spectrum here. That discrete spectrum is preserved by the KdV equation. And therefore, the KdV equation indeed does have infinitely many first integrals, or infinitely many conserved quantities. There is, of course, a problem with this argument. Well, first of all, we don't know why these conserved quantities are in involution. Why pairwise Poisson brackets of these eigenvalues are equal to 0. And that is clearly difficult to show directly. And another related problem here is that, well, we found conserved quantities, but somehow they're not very explicit. Because recall that what we started with, we had this nice functionals that are conserved, like the integral of u squared. The next one was the integral of u cubed minus 1/2 ux squared. These were very explicit, but now we get spectrum of the Schrödinger operator. There's no way we can write this in an explicit form. We cannot express these eigenvalues in terms of u. So even though theoretically this does give us an infinite sequence of conserved quantities and sort of shows that it's an integrable system, we will actually want to take a different approach that will give us an explicit infinite sequence of first integrals, which moreover we'll know are automatically Poisson commuting. And that's the thing that we'll do next time. So we'll take a slightly different approach here. Instead of using the fact that KdV is a Lax equation, what we'll use is that, so it's an observation that goes back to Franco-Magri, is that we show that KdV is a Hamiltonian system. We'll show that actually it can be written as a Hamiltonian system in 2 different ways. And that observation will negotiate to extract infinitely many conserved quantities that are actually automatically in involution.
Those operators, yeah, or something.
Well, there'll be no need for those, but implicitly, yes.
It's Magri-Morosi.
Well, the first paper on KdV is actually by Magri himself. But yeah, then he developed that thing into a whole theory, which will not be very relevant for the KdV equation. Sort of, the idea will be based on his. My exposition will be based on his original.
But it works also for finite dimensional Hamiltonian systems.
That's right. Yes. So the Magri-Morosi stuff is mostly about finite dimensional systems. Okay. So I think I'll just stop here for